Greetings again, good afternoon. We will have the fourth lecture of this series of 6 lectures. We discussed the Eisenwood-Wigner time delay in the previous class. We will now discuss a different criterion altogether to come at the notion of time delay. It will turn out to be, it is completely equivalent to the Eisenwood-Wigner time delay. That does not change the fact that it is different, but also intuitive in some sense. It is a nice way of introducing time delay, and it will give us a form which is particularly suitable to demonstrate that self-adjoint operator, which every observable has, it should have a Hermitian operator representation in quantum mechanics if it is an observable. A self-adjoint operator for the Eisenwood-Wigner, or what we will refer to as the Eisenwood-Wigner-Smith time delay, is representable by a Hermitian operator, and then we will get into applications in auto-second photoionization time delay. So, here are a few papers which are of some interest in this context, and this is a paper by Fetich, Becker and Milosevic. The title is "Can we measure the Wigner time delay in photoionization experiment?" And the conclusion of this paper is that it is not possible to measure because of reasons that the authors have advanced. This paper was published on the archive almost 2 years ago in 2022, but it has come out in print in Annals of Physics just a few weeks ago, just about 2 or 3 weeks ago. It is published, and there is a paper by Chris Green which is in response to this, and it shows that in fact the photoionization time delay is measurable. And then along with Saurav Banerjee and Steve Manson, we have a paper in the Canadian Journal of Physics which came out I think just about a month ago, which is about the measurability of Wigner time delay. So, there are interesting aspects to this issue, and these are the ones that I will discuss in today's class and also in the next 2 classes. So, this is the point of our consideration, that the photoelectric effect experiment which you might have done in your high school or undergraduate lab, that photoelectrons are emitted when ultraviolet light shines on it, and there is no time delay in this in the theory which Einstein advanced in 1905. But given the fact that the speed of light is finite, although it is very high, it traverses atomic dimension 1 angstrom in just an attosecond, it is very fast. There is in fact a little bit of time delay. The Bohr orbits give you a measure of this, measure of an attosecond. One Bohr orbit in the ground state 1s of hydrogen atom to traverse the circumference is about 150 attoseconds, 152. However, as I mentioned yesterday also, Bohr orbits are not, they do not really exist. It was a nice model, and I am reminded of this very nice book by Banish Hoffman, The Strange Story of the Quantum, in which he has a chapter which he calls as the atom of Niels Bohr, and the next chapter as the atom of Bohr-Niels, K-N-E-E-L-S, because the atom of Niels Bohr is of course very good, but then it makes use of orbits, it makes use of trajectories. and trajectory can be defined only if you know the position and momentum at every instant of time. That is what defines a trajectory. It is the locus of a point in the phase space. That is what a trajectory is. And that does not undermines Bohr's contribution to quantum mechanics. I think it is one of the greatest. He did not invent quantum mechanics in the sense in which Heisenberg or Schrodinger did, but he defended quantum mechanics in front of Heisenberg and Schrodinger at the Solvay conference against Einstein's attacks on quantum mechanics. So, Bohr's contributions are enormous, as great as that of anybody else, I would say. I think he was a great hero. So, we are now not talking about orbits, but we are talking about the time electron wave packets take to move around inside an atom or a molecule, and that time is of the order of attoseconds. And we discussed the time delay in scattering in the previous class. We discussed the Eisenberg-Wigner theory of time delay. And what was that theory based on? It was based on very physical considerations that you have got an incoming wave packet which interacts with the target potential, it gets engaged with the target potential, it gets delayed. It may also get advanced if the target potential pushes it rather than engages it, right, and slows it down. It could actually push it. So, there can also be a negative time delay within limits, which is referred to as the Wigner's causality, causality. But the essential point is that there is a delay, either positive or negative, because of an interaction in the target reaction zone. We are now going to talk about a different criterion for time delay, which is due to Felix-Smith. And as you see, Eisenberg's PhD thesis at the Princeton University was in 1948, Wigner's paper in PhysRev in 1955, Smith's paper a little later in 1960. And these are the three names which are associated with the time delay that we talk about, which is the EWS or the Wigner time delay. So, this is the idea in time delay. On the left, you have got a wave packet which is moving at a certain group velocity, and it will eventually be detected at the detector, which is your eye or whatever your detector device is. And the eye expects to receive it at a certain time if it has started out at a certain time. And when the eye will expect to receive it depends on when it has started, also on where it has started, because if it has started from farther away, it would take longer time. Okay? So, if it gets delayed, it is similar to having its starting position farther away in a certain sense. So, the delay translates to a spatial shift. So, they will be equivalent in some terms, okay, depending on the group velocity, right. Now, here is an example of a target which is slowing down the wave packet. It engages the wave packet in the interaction zone, and it has not reached the detector in the same time in which an unscattered wave packet reaches. So, this amounts to a delay, right. Here is another picture which shows that this delay corresponds to a certain phase shift, as if it has started out from behind rather than the original starting point. You get it? Now, here is another picture which represents advancement. the wave packet has already gone through the detector. You see just the last tail piece of the wave packet in this picture, rest of it has already entered the detector. So, this is time advancement, or you can call it as negative time delay. Now, can you measure this in photoionization? Because in photoionization, the reference wave packet, which is the first row at the top in this, does not even exist. Okay? The reference wave packet means the time delay, whether positive or negative, both are with reference to the original reference. It is like the train's timetable that we talk about. It is with reference to the train's timetable that you can say that okay, the train has gotten delayed because it was held up at the previous signal for some time longer than expected, or it reached earlier because the driver accelerated, or whatever be the reason. Okay. But if there is no train timetable and there is no reference wave packet, the first row does not exist in photoionization, then how is it measurable at all? It is a very good question, and we will be discussing this question, and we will figure out that in fact it is measurable. And this is a nice situation. It reminds me of this quote by Bohr, that how wonderful that we are met with a paradox, now we have some hope of making progress. So, he had this on his blackboard in his own handwriting, which is a picture of his signature there, which is why I like this figure very much. As I mentioned, Bohr is indeed one of the most exciting heroes of quantum mechanics. And here are various things which can happen. Electron ion collision, we discussed this figure in today morning's class. This is collision, this is photoionization, and here is a more complete picture, because you can also have a photon and an atom going from left to right is photoionization, we all see that. But you can also have photon atom scattering. So, you can have various reactions, and these are all reversible reactions, you can go any which way. And we are interested in examining the fact that this end product of an electron and an ion is the same whether you go through electron ion scattering or through photoionization, which is this track, okay, which is from the left into the center and then down into this electron ion, which is the same as what we have in this picture. So, these are various things which can happen in these reactions. These are the diagrams that we examined this morning, and we are now asking, how is photoionization related to scattering? I mentioned in the morning also that the processes are related through a symmetry. I pointed out that photoionization would be half scattering, because there is no free electron in the initial state. The free electron is sort of modeled, it is simulated, you pretend that it is there in terms of spherical ingoing waves which cancel each other from every possible direction. Okay? And symmetries are of course extremely important in quantum mechanics. You discuss the rotational symmetry in the context of angular momentum, you have the SO3 algebra which governs it. You also have the dynamical symmetry, as you have in the consideration of the hydrogen atom. The quantum mechanics of the hydrogen atom has got a very interesting degeneracy, which Schrodinger equation does not quite explain, but it is there. And that is the dynamical symmetry comes from the quantization of the Pauli lens vector. And then The symmetry which will be of direct interest to us is the PCT symmetry. These are discrete symmetries which together is a symmetry operation. This is a cornerstone of the standard model of physics, the PCT theorem, and these are discrete symmetries, and the one that will be of interest to us for today's discussion, rather tomorrow's maybe, is the time reversal symmetry. And now we come to Smith's criterion of the time delay. So, we are going to consider two kinds of wave packets, states phi and psi. Phi are the unscattered waves, those are the states of free particles. The free beam comes and hits the detector, nothing is happening in between. The other is the scattered states, in which case the incident beam of projectile interacts with the target and then there may be a delay or an advancement. And these states evolve in quantum mechanics according to the time evolution operator. So, there is a time evolution operator which is a unitary operator, this u. So, the free particle state at time t evolves from the free particle state at t equal to 0 through a time evolution which is represented by this operator, and this operator consists of e to the minus I h t over h cross, as you would have learnt in your first course in quantum mechanics, and the Hamiltonian over here is nothing but the kinetic energy operator, because there is no interaction, it is a free particle. So, the only part of the operator of the Hamiltonian is the kinetic energy part, that is T. The scattered states also evolve unitarily from the state at t equal to 0, which is represented by the equation in red. So, psi at t equal to 0 represents the free particle state, the state at t equal to 0. As t goes to minus infinity, this would not be really different from the free particle states. Okay? But the unitary operator, the time evolution operator, will consist of a Hamiltonian which is not just t, but it will be t plus v. Okay? So, now let us represent this using this diagram, and you have got on the left t going to minus infinity. We consider scattering to take place now at t equal to 0, and at t going to minus infinity you had free particle states, including those which would eventually get scattered. So, those which get scattered correspond to the free particle states, they meet in t going to minus infinity, they would meet also as t goes to plus infinity, because they will be far away from the interaction zone. Of course, if the interaction itself is like 1 over r, which goes to 0 only as r goes to infinity, then you have different things, which is why Coulomb scattering has to be dealt with differently, and the Coulomb phase shift is also estimated using different techniques, which I will not get into, but that is something that you should certainly study. So, here so you have the scattering states which are represented by psi, the red color, and the unscattered states which are represented by phi, which are in the blue color. And you have the free particle states from minus infinity, the scattering, if at all it is to be there, would be here at t going to 0, and the free particle states would also move to t going to plus infinity, and this picture models or mimics the scattering process. But it also shows that from phi you can go to psi. So, from the free particle states you can go to the psi, to the scattering states through these operators omega minus and omega plus after the scattering and omega minus before the scattering, and these operators are known as molar operators in quantum mechanics. We normally deal with the scattering operator, but I will introduce that also in a minute. So, here are our unitary time evolution operators. The molar operators produce the scattering states from the unscattered states. So, here the lower track is the unscattered, the upper track is the scattered, and you can go from the lower track to the upper track using these molar operators. Okay. What does the scattering operator do? It produces the outgoing states from the incoming states. So, the scattering operator has a different function. It produces the outgoing states from the incoming states. The molar operators produce the scattering states from the free particle states. But obviously, there would be a relationship between them. So, these are the relations that we have gathered so far. You would expect them to correspond to each other as t going to minus infinity, and this is some neat mathematical way of expressing it, but I think you already get the idea. So, in the limit that t goes to minus infinity, there will not be any difference between the phi and psi, because they would start out at minus infinity. The wave packet does not know that it is going to get scattered. So, these are the molar operators, and the scattering operator gives you the outgoing waves from the ingoing waves, and that tells you that you can represent the scattering operator in terms of the molar operators, and that is a very simple relationship that pops out of this discussion. And I am now going to refer to Smith's paper in 1960, where he talks about a lifetime matrix in collision theory. This is a phys rev in 1960, and this is Smith's criterion of estimating the time delay. What he says that the time delay would be given by the excess number of particles near the scattering center. If you divide it by the ingoing flux, okay. If this is not the same, it will be a measure of the time delay, because time delay is because there is some excess accumulation in the target region. So, if the target is engaging the incoming beam, then it is holding it up, and in that sense it would give a measure of the time delay. So, it is a very intuitive idea that represents time delay, and on the face of it, it is not obvious that this is going to give us the same criterion for time delay that we got from the Eisenburg-Wigner theory, which we discussed in the previous class. What did we get from the Eisenburg-Wigner theory? That the time delay is given by the energy derivative of the phase shift. So, that is a completely different idea, and here we are talking in terms of the charge densities which accumulate. So, if there is more charge density than what you expect, then there is a delay. This could be negative also, so which will correspond to time advancement or the negative time delay. So, this is Smith's criterion. It is obviously distinct from the Eisenburg-Wigner, but it will turn out that the time delay from Smith is exactly equal to the time delay from Eisenburg-Wigner, which is why we end up referring to this as the Eisenburg-Wigner-Smith time delay. And we will deal with these states. So, our wave functions are functions of space and time. These are stationary state wave functions. They have e to the minus I omega t time dependence. And then there is a radial part, there is an angular part, which are the usual spherical harmonics. We consider spherical symmetry. And as we do in scattering theory, it is easier to work with differential equations not for the radial function capital R, but for u, which is small r times capital R. So, you get simpler equations, and we do this in quantum mechanics all the time. So, we set up differential equation because corresponding to the original equation for psi, you separate out the angular part from the radial part, have a radial equation for capital R after eliminating the angular part which goes into the usual spherical harmonics. On the radial differential equation, you rewrite in terms of a corresponding differential equation for u, and then solve the differential equation for u. And you can write the solutions in a basis set. Now, any basis set works. All you need is a linearly independent basis. It can be sine kr, cosine kr, it can be e to the I kr, e to the minus ai kr, it can be some ul plus, ul minus. So, any linearly independent basis, and the basis set which is appropriate for the Lth partial wave, because mind you, the incident beam is represented by a plane wave which is a superposition of all the Legendre polynomials, L going from 0 to infinity. Okay. The functions for higher L are obtainable through a recursion relation using the previous L. So, that for UL is obtainable from UL minus 1, that for UL minus 1 is obtainable from UL minus 2, and so on. There are these recursion relations which are well known in quantum mechanics and in the mathematics of differential equations. So, obviously, everything can be known from the solution for L equal to 0, which means that you do not even have to solve the problem for all values of L, you just solve it for L equal to 0. So, that is good, because then the centrifugal term which is L into L plus 1 by R square, you can throw that term and your differential equation becomes simpler. You solve it for L equal to 0, and then using the recursion relations you get the solution for L equal to 1, and then L equal to 2 and 3 and 4 and so on, right. So, that is the method of getting solutions.